Algosim is an advanced mathematical software application for Windows. It's like an advanced graphing calculator. Let's try it out. Here we can perform simple calculations, such as 1 plus 1, which unsurprisingly equals 2. Or we can compute the sine of pi divided by 3, which equals half the square root of 3. We can use variables. For instance, if I assign a and b the values 2 and 10 respectively, then a raised to the power of b will equal 1024. I can also create a function. For instance, f is a function that takes a number x and returns x squared plus 1. Then f of 6 equals 37. Algosim doesn't only support real numbers, but also vectors and matrices. For instance, if I press Ctrl-Shift-V as in vector, I get the vector brackets. And now I can enter a vector such as the three-dimensional vector 2, 0, -1. And I can compute the cross product with -1, 1, -1, say. Or a matrix. Let's compute a random integer matrix of size 5, and the elements should be integers between 0 and 10. Here we got one. We can compute the determinant, or the trace, or the eigenvalues, or we can perform a QR decomposition. Here Q is this matrix and R is this, and of course A equals Q times R, essentially. And the point here, of course, is that Q is unitary and R is upper triangular. The syntax of Algosim is made to mimic very closely the notation used in ordinary mathematics. For instance, to compute an integral, I use an integral sign. So the integral of sine x, where x goes from 0 to pi, of course, is about 2. Or the integral of e to the power of minus x squared, where x goes from, say, -10 to +10, that's essentially the square root of pi. We can also compute sums and products, such as this very familiar sum, the sum of 1 over k factorial, where k goes from 0 to 100, say. That's, of course, the Taylor expansion of the exponential function at 1, so it's e. As another example of Algosim trying to mimic the syntax used in ordinary mathematics, let's try to plot a region in the plane. So we ask it to plot sine x to the 4th should be less than y, which should be less than sine x squared from -pi to pi. In many computer languages, this would be a syntax error, because this part should be a boolean, and a boolean cannot be compared to a real number. But in mathematics you often combine inequalities like this, and this is supported in Algosim. So here we get a nice region in the plane. As another example of how Algosim mimics the notation used in ordinary mathematics, consider this small program which draws a two-dimensional surface in 3D space. First I have a rectangular, actually a square region in the UV plane, And then I apply a function to this region. This function takes a two-dimensional vector and creates a three-dimensional vector. So essentially I have a parameterization function and a parameter plane region, and then I compute the image of this parameter plane region under this parameterization function. And as some of you may already have noticed, this will plot a torus. But the Algosim language is not only supposed to mimic the notation used in ordinary mathematics, it's also designed to be useful for various kinds of computations. As an example, let's create a list of prime numbers. This notation is the set from 1 to 1 million. As real numbers with some predefined resolution. If I add comma 1, I explicitly set the resolution to 1, so 1 is the distance between consecutive elements in the set. So I get 1, 2, 3, 4, 5, up to 1 million. And then for each integer in this set, I apply the prime function, which simply returns the nth prime number. So I get a lot of prime numbers, and now I want to obtain various particularly interesting subsets of P. So I want to filter, and the filter function takes a predicate, which is a function that takes a prime number and returns true or false. So it takes P and returns something. Let's denote by D the digits of the prime number. And then we may require, for example, that the sum of the digits equals the product of the digits. So here are the prime numbers less than or equal to 1 million, with the property that the sum of the digits equals the product of the digits. Or as another example, I may require that the sequence of digits is equal to the reverse of itself. Here, clearly, we only have the prime numbers whose digit sequence is the same no matter if you read it from left to right or from right to left. As a second example, let's load Alice in Wonderland. Can make the window slightly larger. Now we can extract the words of this text, and we can obtain the frequencies of various words. We can sort this array according to frequency, which is the second member. So the second member can be obtained by this simple anonymous function. And the minus sign makes sure that we get the most frequent words at the top. So apparently the most frequent word is the, followed by and, to, a, she, of, it, said, I, Alice, and so on. And we can try to plot this in a bar chart. Maybe only the first 20 words. So here's a bar chart with the 20 most frequent words in Alice in Wonderland. Algosim is particularly suited for various kinds of data visualization. We have already seen a few examples of that, but let's focus a bit more on this topic, starting with two-dimensional visualization. So we can simply ask Algosim to plot a curve or other region in the plane, such as y equals the sine of x. And we can stop here for a moment and try to export this image. We can export it as a bitmap or as a scalable vector graphics image. But by default, this curve consists of discrete points. And if you want to export such a nice curve as a SVG file, it's better to use a polyline instead of point markers. So I will change that. Now let's try to save this. On the desktop, I can call it sine curve.svg. Sine curve. We see that it's a pretty nice scalable vector graphics file. It's scalable, so you can zoom how much you want without losing any quality. And if we look at the source code, we can see that it's pretty nice code. And as we already have seen, we can also plot regions. And these regions may be defined by a chain of inequalities. For instance, here's the area below the cardinal sine square. Of course, such an image can also be exported as an SVG file. Again, in vector format. Algosim can also plot implicit equations such as x4 plus x3 times y plus y4 equals inverse tangent of x plus y. We can also plot curves specified by parameterization. For instance, will give us a nice familiar curve used in road and railway construction. Or we can plot any two-dimensional set obtained in any way. For example, we can take a square in the plane and consider this like a region in the complex plane and apply a complex function to this region. So the real and imaginary parts are mapped to, for example, x plus y times I to the third power and then convert it back to a real vector. This should give us a nice leaf-shaped set because of the properties of multiplication in the complex plane. As a final example of two-dimensional visualization, let's create a scalar field. So f is a function defined in the plane, returning a number for each point in the plane. In order to plot several objects in the same diagram, we need to give the diagram a name. We can call this one field. Actually, we can put this next to the console. First, we can create a heat map. The heat map function takes the field and the region we want to plot, say from -1 to 1 in both axes. And we can use light blue as the color scheme. In addition to a heat map, we can also ask Algosim to draw a contour plot. So these are the curves of equal value of the scalar field. We can also try to draw the gradient vector field. The gradient vector field of a scalar field is a vector field giving the direction at each point in which the field increases the most. And to do this, we can define a gradient operator. So the gradient operator takes a scalar field and returns a vector field. So f here is a function, a scalar field. And the returned value should also be a function, a vector field. It's a vector field in the plane, so x and y, mapping to a vector in the plane as well. The components of this vector are simply the partial derivatives of f. So the first one is the partial derivative f t comma y, where t has the value x. And the second component is the partial derivative with respect to y. So f x comma t, where t has the value of y. And then we can use this operator to create the gradient of our scalar field, which is a vector field. And we can plot it like this. But now let's have a look at three-dimensional visualization. A very simple example is just drawing a surface, a two-dimensional surface in three-dimensional space. And we can specify one using an equation in the Cartesian coordinates, such as z equals sine x squared divided by 10 plus y squared divided by 10. A very simple surface. We can remove the axes if we don't want them. We can also create a colored surface if we also specify the color of each vertex. And of course we can also create a surface by means of parametrization. So here I have a parametrization function f, takes two coordinates and returns a point in space, and then we plot the surface, which is the image of a rectangular parameter plane region under this parametrization function. As a final example of basic three-dimensional visualization, let's try to draw a Möbius strip with its normal vector field. To this end, I first define the function nf, which takes a parametrization function for a surface and returns the surface normal vector field. Then I first draw the surface itself, the Möbius strip, and then the vector field. As a more advanced example, let's create a word cloud of the most common words in Alice in Wonderland. The graphical user interface of Algosim is highly customizable. You can create various panels and then use drag and drop to move them around. There are a few predefined layouts, and you can toggle between those using the F4 key. So if I press F4 one time, I get a list of variables, a task list, a debug log, and a clock. If I press F4 once more, I get a full IDE with identifiers, task list, a list of windows, a list of visual objects, the console, the help browser, debug log, and clock. To give an example of a particular layout you may use in a particular situation, I have a program called uTorus, which I have now opened in the program editor. And you can see that the program editor is a text editor with syntax highlighting and optionally abstract syntax tree. This program will animate an umbilical torus and also highlight a particular point on the surface, as well as the parameter plane coordinates of this point. So let's run this program. And then we can put the actual surface here, for instance, and maybe the parameter plane plot here. So then we have our umbilical torus here and a particular point highlighted. And here we can see the u, v parameter plane coordinates of this highlighted point in a named window, suitably called parameter plane. The Algosim environment also allows quite a lot of introspection, in the sense that you can programmatically query and modify the environment. For instance, now I have a program called red, which will take all the XY plots and make them red. So if I run this program, you will see that all my XY plots became red. You may have noticed the built-in documentation viewer. This fully documents the Algosim system and all its about 850 functions. For instance, it documents basic functions like the sine or the inverse hyperbolic tangent, as well as language functions such as frequencies and sort and so on. It's worth pointing out that we have only scratched the surface of what Algosim can do. In addition to all the things we have seen already, we can also work with sounds, MIDI music, and images, for example. Using the documentation, we can have a quick look at the sound functions. For example, append sound. Or scale amplitude.
London, 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 London.
And a quick look at the MIDI functions. And an equally quick look at the pixmap functions, such as adjust HSV, adjust RGB, draw rect, and random scanline rotation. Now it's high time to look at the source code behind Algosim. Algosim is entirely developed in Delphi. No third-party components are used. I only use the Windows API and the Delphi runtime libraries. One benefit of this is that the application becomes rather unbloated, and we see that we have pretty decent startup times. And if we have a look at the executable, we can see that it is pretty slim. It's 19 megabytes. And that's actually all there is, because this DLL file, for instance, only contains sample data such as the text of Alice in Wonderland and various sample bitmap and audio files. The fact that I don't rely on third-party code also means that I get full control over everything, and I don't inherit any bugs or quirks from external sources. Now let me just open up a few panels here. As we have seen, the Algosim graphical user interface consists of various panels, And the most common panel type is probably the text editor panel, which is used for consoles, documentation, program editors, and a few other instances. This text editor apparently supports syntax highlighting and stuff like block selections and multiple carets and OLE drag and drop. And of course it is also fully developed in Delphi. This is not particularly beautiful code because it's pretty old. I think I wrote the first version of it maybe 20 years ago. But it works. If we try to close this console which we have edited, we get the confirmation dialog. These dialog boxes are implemented using the Windows task dialog, but the T-task dialog shipped with Delphi is rather verbose, and therefore I've created a fluent interface to it called task dialog message box. So I only need to write TD and chain properties of the dialog I want to create, and then I execute it. And very recently, this task dialog message box interface was added to Getit, so anyone can use this interface in their own applications. When it comes to visualization, Algosim uses a handful of custom components. For instance, the two-dimensional visualization control, which is used for two-dimensional graphics, such as this one. This is based on Direct 2D, so it's not plain old-school GDI, but slightly more modern Direct 2D, which gives me anti-aliased lines, for instance. And performance is pretty good. As you may know, it is pretty simple to use Direct2D in modern Delphi applications because the runtime library contains support for it. As we saw earlier, this diagram control allows you to export images as scalable vector graphics images. And this is using this SVG builder class that I made for this purpose. This also uses a fluent interface, which makes it very convenient to use. I simply have an SVG builder instance and then apply commands to it. The 3D visualization control is based on OpenGL, the Open Graphics Library, so it is fully hardware accelerated. So basically I need to create a vertex shader and a fragment shader and then pass those to the graphics card so that the graphics card can do its magic. Actually, I would say that Delphi is almost an ideal language for a project like Algosim. It creates native Win32 binaries in this case, and you get excellent performance and you get access to all the goodies on the platform, such as Direct2D and OpenGL hardware acceleration. I also make use of many Delphi language features introduced in the last couple of decades, such as operator overloading. Here you can see my record type used to store complex numbers. And you can see that I overload the plus, minus, multiplication, division operators, and so on. So essentially I extend the Delphi language with my own types, making them as easy to use as the built-in types. I also make extensive use of class hierarchies. Algosim is very much object-oriented. Here, for instance, you can see the class hierarchy of panels in the user interface. By placing code at the very right level, I get a lot of functionality for free. It's almost like the program writes itself. Similarly, the data types and objects used in the Algosim language are also part of a class hierarchy. And the functions of the Algosim language, well, they are too part of a class hierarchy. Let's have a closer look at this. In this file I implement all the about 850 functions in Algosim. As you can see, each function is a class and they all derive from TAS function. And using a clever class hierarchy, I can save a lot of code. For instance, I have a lot of functions that take a date-time object and a parameter, such as add milliseconds, add seconds, add minutes, add hours, and so on. These functions all derive from a tTime1parameter function class, so that I can implement all these functions with the least code possible. I basically only need to map a pointer to the appropriate underlying Delphi language function. The Algosim help system is based on a custom markup language that I created for Algosim. And you can actually see the source code behind each page by right-clicking and selecting Show Source, or by pressing Ctrl-U like in your browser. If we try that here, we see the Algosim markup language used, with a header indicator, and here is a block of Algosim code that I execute. So I don't hard-code the number of functions and operators and build time. Instead, I use the Algosim language to dynamically generate these. An even better example of that, here I have a list of date and time functions. Again, this is not hard-coded. It would be a nightmare for me to update this manually every time I release a new version of Algosim. Instead, you see that the ASML markup of this file contains the header, a line of text, and then a small Algosim program. I obtain all functions and then I filter them. I only keep those whose category list contains datetime, and then I format them as a hyperlink like this and create a table grouped by 3 elements. The automatic build system of Algosim also uses these facilities to create the hypertext version of the documentation. Finally, something that's very important to me is quality. I don't want to make software containing bugs or quirks or anything. But that's not an easy task, and to help, I have added a system of automatic tests that you can run. There are about, I think, 40,000 handwritten automatic tests. And we can see these self-tests here. Unsurprisingly, this is a pretty long file. I think it's 67,948 lines. And here I have all my automatic tests. Anyone can explore the source code of Algosim for themselves, because the entire source code is available on the World Wide Web. I should point out, however, that while Algosim is completely free of charge for personal or commercial or any kind of use, and the source code is freely available on the internet, Algosim is not strictly open source software. So it's basically ordinary copyrighted software, but absolutely free of charge and with all source code available.